question, and we went as far as question 4. So we are resuming on question 5, and then we go down like that. But we're not going to be answering all the questions, especially if we find a question that is using a principle that we've already looked at. Those questions will be skipping them. They will be for your practice and perfection of the concept. So question 5 reads, a galvanic cell whose cell reaction is this as a cell potential of that. What is the maximum electrical work that can be obtained from this cell per mole of ion? So we are answering this question in relation to the ion. So the ion 3 ion, the one that is being reduced. So what we're going to do here is first we break down these two this equation into half equations. So what are the half equations of this particular question? So your half equation will be, you write Fe3 plus, okay, Fe3 plus, and then since the charge has reduced, you're going to put plus an electron, and then the production sign, this sign, this sign after you've written electron, then you write Fe2 plus. Okay, so that is your reduction equation. And then you can now write the oxidation reaction for zinc. Zinc being oxidized. So you write zinc and then you put the arrow giving you zinc 2 plus 2 electrons, because zinc requires, if you check, the oxidation state of zinc in the metal is 0 and the oxidation state of zinc in aqueous solution is 2. Therefore, for the oxidation states to be the same, we write 2 electrons on the right. Now, the reduction equation is not balanced, meaning it has to be balanced. So that 2 you are seeing in front there, this 2 is what was balancing. So you multiply that one throughout by 2, you're going to have 2 ion plus 2 electrons plus 2 ion 2 plus ion. This simply means that from this equation, we now know the number of electrons that are being transferred as the zinc is being oxidized. So from here now, what you're going to do is you will write the free energy equation. The free energy equation is the same equation that you do when you are calculating work done. At maximum, work done, W is equals to G. Okay, at maximum, work done maximum is equals to G max. So meaning the equation that you're going to use for free energy is the same equation you are going to use to calculate work done. So the equation for free energy is G is equals to negative NF electrode, NFE cell. Now the NFE cell is the electrode potential of the cell. Okay. Once you have written that, now you can put in the values that come with that. So you have minus 2 electrons as the number of electrons being transferred, multiplied by the Faraday constant, which is 96,500 or 96,485. Actually, most of the times you are to use 96,485. Not 500. So 96,485 there is what you're going to use. 96,485 as your Faraday constant. And then the electrode potential of the cell has been given in question as 0.72. So from there, you can compute. The answer you're going to get is going to be in joules, and the units thereof are going to be per mole. So what answer are you getting when you do that particular calculation there?
$138,938.4.
Positive, negative?
Negative.
Okay, so your answer is negative. So negative, the answer that you've obtained, that simply means that is the work done by the cell. Okay, whenever work is done by the cell, the sign is negative. Whenever work is done on the cell, the energy work done is positive. So that simply means that is the maximum work done in that particular equation for that particular question. Okay. So we move on to question 6. Calculate the maximum work available from 50 grams of aluminium in the following cell with when the cell potential is 1.5. So you have been given aluminium metallic. So your half reaction there, start. Your half reaction for that question will be aluminium, and then the aluminium producing aluminium 3 plus 3 electrons. Okay. So aluminium solid giving you aluminium 3 plus 3 electrons. And then there they are saying note that oxygen is reduced to water. So oxygen is being reduced to water in that particular reaction, but we don't really need to mind about the oxygen, but irrespective of that, I think I can take you back to the table for the potentials. So let me just quickly find the table for the potential. Okay. So this is the table that we have for the potential. Oxygen giving you, there are two reactions. There's a reaction where oxygen gives you that. Now, when oxygen is reacted with this, it gives you permanganate. Okay, there's oxygen plus hydrogen giving you permanganate, oxygen plus water giving you the hydroxide. So where is the other oxygen? This oxygen here. Oxygen plus that plus 4 electrons giving you water. So you have that equation. Oxygen plus hydrogen, okay, plus 4 hydrogen ions to give you plus 4 electrons to give you 2 H2O. Okay. So this is the equation you're going to write. Now, if I take you back to the question doesn't want you to do a calculation depending on the reaction equation. The work done is not going to be calculated as per reaction, moles of reaction, no. Meaning the moles of electrons we are going to be looking at in this particular question are not the moles of electrons that have been transferred in the entire question, no, but the number of electrons that have been transferred by the aluminium. That's why the mass that has been given is for aluminium. So in this particular case, you actually do not need to balance your equation, because when you balance your equation, you'll be looking at the total number of electrons that are being transferred. And that will mean you are looking at the question from the total number of electrons perspective. But in this particular question, what we want to look at is how much aluminium is able to produce. So we will concentrate on the moles of electrons of aluminium that are being transferred. And if you look at the half equation for aluminium, the moles of electrons of aluminium being transferred is 3. So we will do moles of electrons of aluminium as 3, but we have been given the mass of aluminium, meaning aluminium was not at standard. And since aluminium is not at standard, you are going to use the moles of electrons that are resulting from 50 grams of aluminium. So what we're going to do is let us find the number of moles of aluminium that are in 50 grams. So you're going to say number of moles N is equals to mass divided by molar mass or atomic mass, which is equals to 50 divided by the atomic mass of aluminium. The atomic mass of aluminium is let me just see if I can find. Okay, so the atomic mass for aluminium, still not very visible. Okay, the atomic mass for aluminium, aluminium is in this group. (26.98). 26.98. So 50 divided by 26.98. What is the number of moles that you're getting from there?
1.853.
1.853 moles. So those are the moles of aluminium that you have available. So now find how many electrons those number of moles of aluminium can fasten. So 1 from the equation written, okay, from the equation that you have there, 1 mole of aluminium produces 3 electrons. Therefore, 1.853 moles of aluminium will produce X electrons. So find the number of electrons. Therefore, X is going to be equals to how many moles of electrons will that produce?
5.55.
Okay, 5.5596. Okay, so 56 moles. So those are the moles of electrons that are being transferred in that particular question by aluminium. Now, since we have found the number of moles that are being transferred, we can now easily calculate the energy or the work done, because we already have the equation G, which is the same as work done, W. So W is equals to minus NFE, because you are calculating for work done. So the symbol you use is W, though it is the same as free energy. So W is equals to minus NFE. You know what N is, you're from calculating, you know what F is because it is given, and you know what the electrode cell potential is because it is given in the question. Therefore, the question is done. From here, you can further calculate other things that, you can calculate for yourselves, even with ease, with no challenges. So straight away move on to question 7, unless there are questions, of course. Okay, so question 7.
Sorry, sir, I've got a question.
Okay, Joshua.
For when finding the maximum weight, the value of N, are we supposed to use the number of moles which we found by when dividing 50 divided by 26.8? Is that the value of N which we should use?
No. You are from
No.
calculating the number of moles of electrons transferred after you have found. When you divide 50 by 26.98, that is the number of moles of aluminium that you have available. Now you want to find how many moles of electrons will that number of moles produce. And then you already have there that from the equation you've written, 1 mole of aluminium produces 3 electrons. How many electrons will 1.853 moles produce? So there is that calculation you're doing there. When you cross multiply that, it gives you 5.56 moles. So those are the moles of electrons. In short, the number of electrons that will produce. So when it comes to the work done calculation, N is going to be 5.56 and not any other number. Hope that's clear.
Yes, sir, it's clear. Thank you.
All right. So we move down to question 7. Using standard reduction electrode potentials, calculate standard free energy change at 25 degrees Celsius for the following reaction. So you have this reaction here, 3 copper plus nitric oxide plus that, giving you that, and 2 and water. Okay. So we are going to break down this given equation into half reactions so that we can be in a position to calculate the cell potential. What is the cell potential here? So this reaction has been balanced and stuff, but we do not know what the cell potential is. For us to know what the cell potential is, we need to break down the equation into half equations. So we start. You're going to write, since copper on the reactant end is solid, and if you check on the product end, it is +2. The oxidation state has already changed. This simply means that copper is being oxidized. So we write the oxidation half equation. So the oxidation half equation is going to be copper to produce copper 2 plus 2 electrons. Okay, why 2 electrons? Because copper is coming from a point where it is 0 to an oxidation state of +2. So from an oxidation state of 0 to an oxidation state of +2. Okay, so that is what copper is doing. Then the other one, therefore, is going to be reduced. So if you check nitric oxide, not oxide actually, the nitrous ion there is so we can check this reduction here, where this is being reduced to that by just straight away going to the table So every time such a question comes, they will give you a table. So we just start looking for nitric. So the oxidation state of nitrogen is changing. That is why it is being reduced in that one and in the other one. The oxidation state of nitrogen is changing, and we don't have that radical here. So meaning we need to look it up for us to continue with the answers. But we have for copper here, copper plus 2 copper electrons, the potential is 0.34. So in our question, it has been reversed. So here it is positive, it has to be negative, so it will be negative 0.34. Remember, here it is written in its reduction state. So reduction positive. But the way we've written it in our equation is it has been written as oxidation. So since it has been written as oxidation, it has been reversed. Therefore, we reverse the sign from 0.34 to negative 0.34. But then we do not have the one for nitric, the nitrous ion here. There is nothing for the nitrous ion, but going back to the question, it will be the nitrous ion plus H2O. Is it H2O given that plus H plus, then to give you NO. Okay, so you are writing this one, NO3 minus plus H plus to give you NO and the water molecule that is at the far end. And then you are going to put the number of electrons on your left. So there will be a number of electrons being transferred there. So for you to now know the exact number of electrons that are being transferred in this particular question, though they will give you the number of electrons being transferred in this question, you can look at the oxidation state. Okay, you can look at the oxidation state. So if you have written electron plus NO3 minus plus H plus to give you NO plus H2O, if you have written that, you can actually now find the number of electrons that are being transferred by looking at the oxidation state of nitrogen. So on your left, the oxidation state of nitrogen is going to be found by saying X plus, in brackets, minus 2 multiplied by 3. Minus 2 is the oxidation state of oxygen, okay? But there are 3 oxygen atoms, so it is 2 times minus 3 is equals to minus 1. The all of this molecule as a minus, meaning this minus there, okay? If you check, there is that minus there. So meaning that is the overall charge on the molecule. So negative 2 times 3 will give you negative 6. And when negative 6 crosses the equal sign, when it comes to the other end, it becomes plus 6. And minus 1 plus 6 will give you 5. So the oxidation state for nitrogen on your left is 5. The oxidation state for nitrogen on the other side, on the right, is going to be, there is no charge. If you check, it's nitrogen gas, so there's no charge. So the overall charge there is 0. Therefore, you have X for nitrogen plus, in brackets, minus 2 for oxygen should give you 0. Therefore, X is equals to 2. So the oxidation state on your left is, on your right, I mean, is 2. So you can check nitrogen's oxidation state on both sides is not the same. On one side, it is 3. On the other side, it is 2. Meaning you have to make that the same. So for you to make that oxidation state the same, you will just add a 2 in front of those electrons, meaning those electrons are going to reduce that oxidation state of nitrogen by 2. And on your right, you're going to have that. So you're going to have 2 electrons there. So electrons, that is what is happening. Anyway, you're going to be given that. You don't need to worry about how to do those calculations, but that is what you're going to have. What I wanted to bring out is when you break down your half equations, the number of electrons should go on opposite sides. Oh, actually not 2, but 3. For it to reach on the oxidation state of 2, meaning 3 electrons. Sorry for that. If you check, it means 3 electrons.
So, but how are you getting the 3?
Nitrogen's oxidation state on your left is 5. On your right, it is 2. So how does the left get to 2? Okay, so how does the 5 get to 2? That's the same as saying 5 minus 2, and it gives you 3. Meaning on your left, 3 electrons are being transferred. That is why the oxidation state of nitrogen is reducing from 5 to 2. So 3 electrons are being transferred. And when this equation is being, when they give you this equation, they'll give you like this 3 electrons plus, actually it will be NO3 plus H plus 3 electrons and stuff. So this is the equation that you're going to have. Okay. And then what you're going to now look at is electrons being transferred. On the copper, 2 electrons. On your second equation, 3 electrons. How many electrons needs to be transferred in total? You have to balance electrons. So you will multiply the top one by 2, the lower one by 3. That will give 6 electrons in total. So that is our concern. 6 electrons are being transferred in this particular question. Once you've established that, everything else that follows is soup. Because from here, like I said, they will give you the cell potential for the other cell. So say this one below, the one we have 3 for the the nitrous reduction, we make an assumption that the cell potential for that particular equation is 0.84. Make an assumption that the electrode potential for the reduction, so you have the oxidation, which is for oxygen, and then you have the reduction, which is for nitrous. So our assumption is that the reduction potential is 0.84. So if that is the reduction potential, therefore we're just going to say electrode cell potential is equals to the potential at the anode plus the potential at the cathode, which is equals to negative 0.34 plus 0.84. So what is negative 3.84 plus 0.84? Negative 0.84 plus 0.84 gives you you guys, are we together?
So for the lower equation, is it supposed to be 1.00?
I don't know. I said I don't have the potential, so I'm making an assumption. But if you've looked up the cell potential, then you can tell us, and we'll use that same one.
We can use 1.00.
Okay.
Then when we subtract the 2, it will be 0.6.
Okay, so 1.00 is the potential for the lower one, meaning 0.6 volts is the cell potential.
0.66 volts.
Okay, so that is the what? The cell potential. Once you have found the cell potential, you already have the number of electrons being transferred as 6. Therefore, you can easily calculate for the potential of the free energy from the free energy equation. Now here, because you have the values that are required. Anyone not clear here?
Sir, how did you come up with the equation for nitrate?
Okay, these equations, usually when these questions come, they will give you the equations. Okay, they will give you the equations here. I think if we keep trying to stick to finding out how the equation is brought about and stuff, we'll just waste time. Because even if I show you how I'll break down the equations, there will be no potentials for those equations. But when a question like this comes in a test, they will give you equations because you need the cell potentials, I mean the electrode potentials for you to calculate the cell potential. Without those, you can't answer this particular question. You can't Google when you are in a test or an exam. You can't ask for anyone to help and stuff. Everything that is needed to be used to answer your questions will be provided for. So if a question like this is to come in a test, they will give you the cell potential for the reduction of copper and for the reduction of nitrogen, the nitrogen gas to nitrous acid. They will give you those. And then you yourself will now be able to tell which one is being reduced and which one is being oxidized by looking at this particular equation as your guide. So copper going to copper 2, meaning this is oxidation. If one of them is oxidation, the other one is definitely reduction. This is oxidation, the other one will be reduction. The potentials are going to be provided for, and the calculations will follow as they are. The only thing you have to do is balance for the electrons. So however way you break them down, so you don't mind the coefficients here. These 3, 2, 8, 3, 2, 4, don't mind about those. Just pick the element, copper alone, and reduce it to copper 2. Because this is what you're going to find when you look at the table. Even there, nitrogen alone, going down to nitrogen gas, and then this as well, just like that. But for the second one, it will be given in the question, because there is a certain value that has to come with the hydrogen ions. So there will be a number there, either 4 or something, 3 or something, and with water as well, so that when you multiply, it goes to these values here. So I can even tell this one at 4 and water was 2. So the all reduction equation here is NO3 minus plus 4H plus to give you NO gas plus 2H2O. And they'll give you the electrode potential for that particular electrode is 1.00 volts. And then from there, you can now balance electrons. After you've balanced electrons, then you go on and you find the cell potential by adding the cell potential, the cell potential by adding the electrode potentials. After you've added the electrode potentials, then you can use the free energy equation, which is G is equals to minus NFE, to find the value of G. That is how you calculate for this particular question.
So, sir.
Yes.
So I'm kindly asking if you can send the recorded video in the group.
Yes, today is the last day, so I will send tomorrow. I send the videos after we are done with the meetings of the week. So today is the last day for this week. Therefore, tomorrow or the day after, I'll be able to send these recordings.
Sir.
Yes, Betha.
What do you replace there where there's a negative N? Do you replace the same 6, or maybe you find the number of moles, what you have done on question 6?
No. Question 6 is different. This particular equation, they've not given you the amount that is used, meaning they use the standard amounts. meaning whatever you get, whatever electrons you get from here are the actual electrons that were transferred. For this particular question, they've given you an amount that is being used, which is different from here. They've not given you the mass of any one of these, nor the concentrations of any one of these. So you cannot start finding the electrons that are going to be transferred like we did in question 6, because in question 6, we were given the amount of aluminium available. So we needed to work with those amount of moles that are going to be available from the available mass of aluminium.
All right, sir. Thank you.
Okay. So copper 1 can act as both an oxidizing agent and a reducing agent, hence it can react with itself. Calculate the equilibrium constant at 25 degrees for this reaction using appropriate values for electrode potentials. So in here, copper 1 is disproportionating. So what we're going to do is we will break it down into half equations. So half equations, the oxidation equation, you write copper 2 plus to give you, copper plus, it is just copper plus on the left, copper plus to give you copper 2 plus plus an electron. That is your oxidation equation. And then we move on to the reduction half equation, which is going to be copper plus an electron to give you copper solid, like that. So those are the two half equations that we're going to use. So what we're going to do now from here is let us find the cell potentials for what we have just talked about. So quickly, in a few minutes, seconds that are remaining before you log in back, we should have already found. So you have there copper 2 plus 2 electrons giving you copper that. That's not what you want. So you have to find where copper 1 is being